you doing, Mr. Chu? How you doing, Donald? Good to have you guys here. We will start at 2:05. That's a few minutes from now. If you're here and you don't want to be shy, feel free to say hi to us in the chat. We will get going in a few minutes. How you doing, Marco? I could tell, Marco. You got that nice name. Marco plays. What's Marco's favorite game to play when we're stuck here waiting 1 or 2 more minutes before we start? Nothing, Marco? You don't want to share with us your favorite game before we start? We get 2:03, but 2 more minutes then I'm going to start. Just give people 1 or 2 more minutes to jump in. Free Fire. Alright. I'll have to check that out. Alright, I'm going to clean some of this up and we'll get started here in about 30 seconds. Alright, we're going to go ahead and get this lesson started at this point. Thanks for those of us who joined us live. If you are joining us on recording, that's great to have you as well, even if you're not live. We have one big goal in this assignment, and it's ultimately to build us. Let me turn the mouse highlighter on. 1 second. Our big goal here today is to build us towards how can we use our understanding of slope and Y-intercept to interpret and problem solve with real-world linear graphs. Well, what we really mean by this are the word problems you see that have linear graphs and where the Y and the X-axis stand for something. Our goal is how do we start interpreting and problem solving with those linear graphs where the Y value and X value stand for something. Your Y-intercept, your slope are still going to be important. Understanding that slopes are built with slope and Y-intercept, this Y equals mx plus b idea remains important. The first 2 problems that we're going to have today actually practice the background skills of how to graph linear equations and how to find equations to match linear graphs. These are the first 2 Khan Academy assignment skills, so we're going to practice those a bit before we get into the real-world graphs. For problem 1, our first situation, they tell us for both linear equations they want us to do a couple things. First, they want us to identify the Y-intercept and the slope, and then also they want us to create a graph once we've identified that Y-intercept and slope. So the first thing, recall, hopefully we've been practicing this for a week now, this Y equals mx plus b idea should be familiar, and I forgot to bring my camera in, by the way, in 1 second. Hi to all of you, forgot to bring that in, sorry about that. If it's in Y equals mx plus b, m is going to be always our slope, and b is always going to represent our Y-intercept. So in this case, I see for the first equation, y equals negative 2x, the negative 2 is in the place where the m should be. So that tells me that my slope here is negative 2. And anytime my slope is a whole number, I can turn that slope into a ratio or a fraction by just dividing by 1, since that doesn't change anything. The y-intercept is represented by the b in this y equals mx plus b form. The b stands for the beginning point, or what value does y start out with when x is 0. So in this case, when I see this plus 5 here, that tells me, hey, if we were to get rid of, if we made x 0, in other words, if we entirely got rid of that negative 2x term, then y would have to be equal to negative 5 if we made x equal to 0. So that tells me my y-intercept here, in other words, my value for y when the x is 0, is a positive 5. And we call the y-intercept the b because it's our beginning point, the first point we probably want to plot. So I'm going to have to plot a y-intercept of 0 and 5, and a graph of negative 2 and 1. So if you were to double click on this graph at home, that will open it up and allow you to edit. I'm just going to plot points directly on it. If it's 0 and 5 for the graph's y-intercept, this point right here, where I'm about to put a red dot, this point represents the y-intercept, and that should really be the first point that ends up on your graph. Now the slope of negative 2 over 1 tells me how the line, since that's the m, it says the movement, how the line will move afterwards from the y-intercept. And that's rise over run. This tells me negative 2 over 1 means y is going to lose 2 units for every 1x. In other words, this graph is going to have to go down by 2 units every time it goes right by 1. So again, down by 2 units and right by 1 unit. And then this new point right here, after I've gone down by 2 and after I've gone right by 1, that new point right here represents the next data point that our graph needs. You could keep going, follow down 2, write 1, plot another data point, and then you'd drag that line through, and you'd end up ultimately with a linear graph that looks something like this. Again, when you make these own graphs at home, it's okay if you just plot the dots. If you want to actually drag that line around and fit it properly, that's totally okay. Just grab the 2 pointy ends of the line when you try to move it. For the next one, if you are watching on recording, hopefully you're trying to do this green one on your own by pausing the video. If you're with us live, I'm going to slow down a little bit, so hopefully you can be getting the y-intercept and the slope and plotting this graph out before me. Again, my job, if I'm going to try to graph the second one, first point I'm going to identify this time when I'm building my graph, I'm going to look for the y-intercept, and I see that circled in green here now. That's got to be my y-intercept for this situation. So that tells me there, since this is the b and it's a -4 or a -4, that tells me that my y-intercept here is going to be a negative value, or -4 at the beginning. The slope is going to be whatever number is multiplied with x, the coefficient of x, and in this case 3/2 is our number that's multiplied with x, so this 3/2 represents the slope. That's the rise over run, which is going to help describe how the line moves after we plot this y-intercept. So first point I'm going to plot here now is going to be that y-intercept, that's the -4, and we're going to put a dot right here. This point represents, for this y equals 3/2 x minus 4 relationship, -4 is its starting point for y if you were to make x 0. The slope of 3/2 means y will gain 3 units, but you need 2 x's to make that happen each time. So you're going to go up by 3 units, but every time you go up by 3 units, you need to have gone right by 2 units. So I'm counting that out on the graph right now, up by 3 and right by 2. And now I'm going to get a new data point right here. I again could go up by 3 more, 1, 2, 3, right by 2, and plot another green point there. And our straight line is going to follow this trend that we see, positively slope by 3.5, or moving up by 3 every time it goes right by 2. That's ultimately what your graph will look like there, with a little arrow on both ends showing that the line, or these solutions, keep charging infinitely in both directions. A quick reminder, we make these graphs because every single point on this graph has an x and a y value, and every time it's one of the points on the green line, that xy pair is one of the solutions that would work in this equation. Alright, hopefully that helps you out. Hopefully you're in good shape on the first Khan Academy assignment already this week to build these graphs from linear equations. Next up, we're going to move to the reverse. What's the second Khan Academy assignment really? And that's problem 2 for us today as well. Here in this case, it's the reverse. They're going to provide you with the linear graph already, and your job is to figure out what is the equation that would match that linear graph. Again, your understanding of slope and y-intercept is very helpful here. That's the key to finding the equation. So my first job is to see where is the beginning point for this purple line. Where is the y-intercept located for the purple line? And I see right here where I'm placing a green dot right now. 1 second. Where I just placed this green dot right here at the -4, that's the location where the purple line crosses with the y-axis. So this tells me what the y-intercept must be for the purple graph. It's at -4. So there's our y-intercept. It's at 0 and -4. And now I also need to measure the slope. That's the other key piece of information I need to get this equation built. Slope measures rise over run. As you recall, we need 2 data points if we want to measure what the slope is on our own. We could use the y-intercept, and I keep following this purple line looking for a second data point. And I want to pick a data point that's right on the corner of a grid box. I see right here where x is 1 and y is -1, the purple line hits a corner here, and there's also a couple other good points there and up there. But I'm going to focus on these 2 right here. And I see to get on this purple graph, or this purple linear equation, I need to travel up first. And then I also need to travel to the right. Specifically, I need to travel up by 3 units. And we need to travel right, but we only needed to travel right by 1 unit. So I've put this +3 and this +1 here to show on this purple line it travels up by 3 units every time it goes right by 1 unit. That's how I know that my slope, and I should have done all of that in red. Sorry, I didn't put it in red to match with slope. But that's what tells me my slope is going to be 3 over 1. So I'm going to plug that info in here, slope of 3 over 1, and a y-intercept of 0 and -4. And if that's my y-intercept and if that's my slope, then I have everything I need to write an equation. An equation's always going to be taking this y equals mx plus b form. And here the m, the slope, is going to get replaced by the 3 over 1. And I'm going to simplify 3 over 1 even further to just 3. Whenever we write equations, we simplify that slope to a whole number if it can be simplified to a whole number. And for the y-intercept, because it's down at -4, instead of adding 4, we're actually going to be subtracting 4. Could write plus a -4, but it's simpler to say -4. So there's our equation in simplified form to match the purple graph. Hopefully that makes sense about how we got there. And if you're at home watching the recording, please pause the video, try to do the next one on your own. If you're with us live, hopefully you can find the y-intercept, the slope, and the equation before you see me show it. So we're going to transition now and take a look at the orange line. My first job, I'm going to try to identify where is the y-intercept for this orange line, and I see the orange line is crossing with the y-axis right here at the point where I just put a green dot. The coordinates for that point are 0 and +4. X is 0 at that point, and y has a value of +4, and that represents the beginning point, or the first solution we found for this orange linear equation. The slope then is going to be measured by rise over run. Again, we'll need 2 data points to measure slope. I'm going to go ahead and use this data point right here. Oh, sorry, I've messed up a little bit. That's text. There we go. So now we're going to switch over to brush this data point right here, and I'm also going to use the y-intercept for the beginning point to measure this slope. I see here that to get from the green dot to the red dot, first we need to travel down on the y-axis and then right. Specifically, we need to travel down by 2 units, and we need to travel to the right by 3 units. When I go right, x is gaining, so I'm going to put that as a +3. And when I go down, y is losing, so I put that as a -2. This shows me here that my slope now for that second situation is going to be -2 for the rise, +3 for the run. Again, -2 over 3. We could simplify that to put the negative sign out in front, because a negative divided by a positive creates a negative, or you could leave that negative attached to the 2 or the 3, but not both. For the equation, once we have the y-intercept and the slope, that's just all we plug in for our mx plus b situation. The m gets replaced by the slope, which in this case is negative 2/3. The b gets replaced by the y-intercept, which is a positive 4. And if you want to be able to make that fraction in the proper Google Docs way, it's a bit of a pain in the neck, but we'll show you. You're going to have to insert or view an equation quickly. I shouldn't have done that, my computer's going to lag. We're going to leave this actually as 2/3 x. And on your screen, if you hit insert equation, you'll see an equation toolbar that will let you insert some of the fractions that you see right here in this equation. Not a big deal, totally okay to leave the fraction like you see it here. Okay, with that, we're going to move on to the second half of this assignment now. Those first two problems really reviewed for us the key skills that you should have been learning from Khan Academy 1 and 2 this week. And now we're going to move on and we're going to look at some of the graphs that have real-world context, or as Khan Academy calls them, the word problems. What I mean by real-world context is now our y value and our x value actually stand for some variable or some quantity that's in the real world. And when that happens, we're going to get some word problems where the sentences describe the scenario potentially, or they ask you questions about what is the story being told by the data on the linear graphs. And at least for me, one of my big keys, I think, is to really first read through the problem and just get a sense of the story of what is the graph generally telling me about. What's the basic summary or the plot summary of the story on the graph? Then I go try to find my question, and based on that question, I dig back into that story, the graph's data, and try to figure out what data on here helps me answer this question. So we're going to read through this question first. I hope it's zoomed in enough for you there. It says a student plugs her phone into a charger. The percentage of the battery's capacity that is charged as a function of time is graphed below. So this is Khan Academy's fancy way of saying when they say as one variable, battery capacity, as a function of the other, they're saying there's a linear relationship between these two, if the graph is a straight line. The time in minutes is directly related to how much capacity or how much charge her battery has. And the y-axis is going to measure the capacity for the battery, while the x-axis I see is measuring how many minutes that battery's been charging for. And as we would expect, the general story is the phone starts off not at a full 100%, and it starts charging up, and the longer she charges it, the more that the charge or the battery goes up in percentage. Question A, our first part, says to us, what is the percentage of battery charge when the student plugs in her phone? I'm going to zoom out just by one so we can see all four problems while we start marking this up. Okay, so I'm going to put this first one, we'll call this part A, we'll call that the red part. And here I'm going to say, what is the percentage of battery charge when the student plugs in her phone? That's really our first question. And if they're saying when the student plugs in her phone, that means after she's been charging the phone for 0 minutes. This is really asking us about the y-intercept. They're really saying, hey, at the beginning, at the 0 minute mark, when she plugs in her phone, how much charged is it? This is going to be represented by the y-intercept. Here, they're kind of really asking about the y-intercept when they say when she plugs in her phone, how much battery charge did it have? And I see that right here, where I put a red dot right now. That red dot represents for us the y-intercept, or at 0 minutes, the girl's at 40% charge. That's what this y-intercept tells us. So part A was really just asking us what is the y-intercept in fact. We knew it was 40, telling us, hey, the girl's phone is at 40% when she plugs it in. Part B, which we'll switch over towards blue now, it says, how long does it take for her to fully charge her phone? How long does it take for her phone to fully charge? That's what part B is asking us. So if the phone's fully charged, they're really asking me here, they're saying, at what point, at how many minutes does it take for her phone to get to 100%? That's really what they're asking us here. How many minutes does it take for the phone to get to 100%? It's almost really asking us for the end point. We don't really have a fancy math name for that end point here. But I'm going to go up here. I see on the graph where it's 100%, and I'm looking across. When does this blue line reach 100%? And I see, let's put a dot there first. Right here where I've put a blue dot, this data point represents 100% charge. That's the Y value. At this data point, it has 100% charge. And how long did it take? I see that it lines up at the 30 mark. So that tells me for this data point with coordinates 30 and 100, it says, hey, if we charge this phone for 30 minutes, that's when it's going to reach 100%. So that tells me how many minutes did it take to fully charge the phone? 30 minutes. Next up, for part C, they ask us, what is the rate of charging when the phone is plugged in? We're going to do this one in green now. We're going to call part C the green one. It says, what is the rate of charging when the phone is plugged in? And whenever word problems ask you about speeds or rates, whenever they say how much does one unit move per another, and this one, how much does the rate charge, how much percent per minute, they're really asking us about slope. And as you recall, to find slope, we need two data points to measure our y change over x change, or the rise over run. And in this case, we already have two data points. I'm going to use those. At the beginning, at the 0 minute mark, it's 40%. By the end, it's up to 100%. So that tells me here, I'm going to go draw a line upwards. That's the phone charging. It goes from 40% to 100%. And to go from 40% to 100%, I must have gained 60%. You see it's at the 40% mark. By this data point, by the end, it's climbed up to 100% charge, so we gained 60% on the y-axis. And to gain that 60%, we want to take a look and say how long or how much run was there to make that happen. And we went from the 0 minute mark all the way to the 30 minute mark, so that tells us it must have taken 30 minutes, an additional 30 minutes, in order for us to charge 60% of the phone. So that's how I'm going to get to my ratio. I see that the phone's charging at 60% every 30 minutes. And that can simplify even further to say 2% per minute. So I'm going to simplify this a little further. 60% every 30 minutes is 2% per 1 minute. And that's really what our slope is at the end of the day here. 2% every 1 minute. And the final question now asks us, the next day her phone is at 20% when she starts charging it. How long before it is fully charged? So our final question says the next day her phone is at 20%. So that's the key to read here. How long before it's fully charged? So if she's at 20%, that means she's got to get 80% more. So I'm going to go ahead and put that. Needs another 80%. And I also know that this phone charges 2% per minute. So if I do 2% per minute, that means I could take the 80% and divide it by 2, because every minute I get 2. So that means ultimately it would take 40 minutes. If I know I get 2% every minute, I'm going to use that rate. If I need to get 80% charged, well, 80 divided by that 2% I get each minute tells me how many minutes it's going to take. In this case, it's going to take us 40 minutes for that phone to charge up 80%. Another way to tell us that this kind of makes sense for our final answer, we know that when the phone was more charged, when it was at 40%, recall it only took her 30 minutes to charge it all the way, and now that her phone's only 20% the next day, it's going to take her a little longer. It's going to take her 40 minutes. Alright, we're going to move to the next one. I do believe these word problems become more complicated. There's definitely a lot more going on. The good and the bad. The good, as Mr. Chu was mentioning with me before, this is really why we study the linear graphs, because this is where it happens in the real world and where you might actually use this math to model something in the world. But it certainly is a bit more of a challenge as the graphs have context in your problem solving now. So please send me emails if you're working on Khan Academy and a little bit stuck and haven't found this super helpful. Alright, I'm going to clean my screen up quickly with the work from the old problem, and now we're going to take a look at the next word problem. For the next word problem, let me zoom down just a little bit, we're told, and this is pulled directly from Khan Academy, Zane is exploring deep in a volcano and starts to quickly climb out when he hears a concerning noise. The graph below shows Zane's elevation relative to the edge of the volcano as a function of time. In other words, Zane's down at the bottom of the volcano, he gets scared, and he starts scrambling up. And that's what we see on this graph. He starts below the edge of the volcano, he's down at a negative height because he's down in the volcano, and then he starts scrambling outwards. That's the story being told by this graph and by the sentence that kind of summarized it. Hey Michaela, awesome to have you with us. I think it should allow you to rewind too, but you might be pretty good on number 1 and 2 and able to just join us live here to see some of the word problems. Always good to have you with us, bud. So part A is asking us, how deep is Zane when he starts to climb out of the volcano? So for part A, I'm going to kind of underline this in red again, and it says, how deep is Zane when he starts to climb out of the volcano? So if that's part A, they really say when he starts to climb out of the volcano, according to the story, that's in the beginning. He's climbing, he's down at the bottom, he gets scared and starts to quickly climb, and the graph now shows that quick climb that he makes. So the beginning is really asking us here for the Y-intercept. That's really all part A is asking you about, saying what is the Y-intercept? And here, we see that this blue line that represents Zane's height at different times, at the beginning, the blue line is down here. Let's put a big red dot there. This red dot represents the beginning, or the Y-intercept for Zane, and it shows me at the beginning of this adventure, or the beginning of this story, he's at negative 25 meters to start. So I'm going to go ahead and label that coordinate just for the future. At 0 seconds, he's at negative 25 meters. And I'm going to go ahead and plug in our answer for part A. Hey, at the beginning, or at the start, 25 meters. I'm going to say deep, and 25 meters deep is what they represent with that negative, 25 below. Could have probably put a negative 25 for my answer, and that'd be fine. So now we're going to move on to part B. And part B asks us, we're going to mark this one up in blue instead. Part B says to us, hey, how long does it take Zane to climb back up to the edge of this volcano? So Zane's panicked, he wants to get all the way back to the top of the volcano's edge. How long does it take him to get there? And it's kind of important to understand here from the context, Zane's climb back up the edge of the volcano, when he gets to the top, he's going to be at 0 meters. The way this graph is built, when he's at the edge of the volcano, that's really what 0 meters represents. It's not down in the volcano at all. And here, I'm going to go ahead and put a nice little dot right here at the 35, where this blue line hits with the x-axis. That represents Zane finishing his scramble out of the volcano. The coordinates there tell us, those coordinates, x is 35, so they say 35 seconds. Now Zane is finally out of the volcano, or he's at a 0 meter altitude, the way we're measuring elevation here. So that tells us it takes Zane 35 seconds. Now I have 2 data points that really make sense on this graph, which is good news, because for part C, they ask us, ultimately, how or what is Zane's rate of climbing per second when he's escaping the volcano? Let's circle that again. What is Zane's rate of climbing per second when escaping the volcano? And we know whenever they ask you for rates, whenever they say something per something else, they're asking you about slope. They're asking you about the rate of change. And to measure the rate of change or slope, I've ultimately got to have 2 data points to measure the rise over the run. And here we have those 2 data points already. At the beginning, at 0 seconds, he's 25 meters below. By the end, at the 35-second mark, we're back to the top. We're at 0 meters. So I'm going to draw in green here a line that goes up and a line that goes to the right. And up represents his climb, and we know from negative 25 meters to the top, to 0, that Zane has climbed there by plus 25 meters. And we also know that he got those plus 25 meters, or it took him from the 0-second mark here all the way to the 35-second mark. So that means it must have taken Zane a total of 35 seconds to climb those 25 meters up. So this data right here, the 25 for a rise, 25 meters gained in 35 seconds of run, tells me my slope is 25 over 35. Our slope there is 25 meters for every 35 seconds. And we can simplify that further. We can simplify our fraction a little bit further. If 25 over 35 is here, I recognize that both of those are divisible by 5. So I'm going to insert a new equation here. And I'm going to put my fraction in. And 25 over 35, if they're both divisible by 5, I can simplify 25 over 35 to be 5 over 7. So that tells me really we're dealing with 5 meters every 7 seconds. You could simplify that even further to say 5/7 of a meter for every 1 second. But it's a little confusing to say 5/7 of a meter every 1 second. I think it makes a bit more sense to use a rate that's a bit larger, 5 meters for every 7 seconds, so they're both in whole numbers. That last part there, I'm going to clean up a little bit of our other work, but now that we know that the speed of Zane's climb is 5 meters per 7 seconds, that becomes the key for part D, which we're going to put in purple for kind of our last example. Here we see part D asks us, how many meters does Zane climb over the course of 20 seconds? And this was not a great problem, clearly, because it's going to work out to a bit of a mess here for a decimal, but that's okay. It makes it more challenging. I messed up a little bit this morning on it. So it says, how many meters does Zane climb over the course of 20 seconds? And what's going to be key here, I'm going to use my rate of 5 meters every 7 seconds. So give me a second to set that original rate of 5 meters every 7 seconds. And if it's 5 meters every 7 seconds, I'm going to set up a proportional relationship here. Something that hopefully looks familiar to what you did with Mr. Neville. 5 meters every 7 seconds, and we want to know ultimately, when is 5 meters every 7 seconds, how much would Zane cover over the course of 20 seconds? So how many meters, I'm going to put an X in 20 seconds, is the same as 5 meters every 7 seconds. And so for this, cross multiplication, you might remember, helps us. If I know a rate, and I want to find the rate, kind of extrapolate it out for a different amount of time, hopefully you recall setting up these equivalent proportional relationships where one ratio is set equal to another. And if there's one unknown, we can cross multiply. So I'm going to go ahead and cross multiply. The X is going to get multiplied with the 7, and the 5 is going to get multiplied with the 20. And that's going to give me a new equation that says 7x is equal to 5 times 20. 7x will be equal to 5 times 20. Let's set up a new equation there. And 5 times 20 I know actually makes 100. So I'm going to have to divide both sides of this equation by 7 to figure out the number of meters. And it turns out it's going to be an ugly fraction. It's going to be 100 over 7 when you do that. And 100 over 7 does not divide evenly. So you could leave your answer as 100 over 7. Or actually use a calculator and see that that comes out to around 14.3 meters. So I'm going to change my 100 over 7 to an estimate. I rounded that decimal off to the nearest tenth, so I put this little wavy sign to say around 14.3 meters. Again, all we did there really, anytime I know an exact rate of change, 5 meters every 7 seconds, anytime the problem says, well, how much for 20 seconds, I can set up this equivalent proportional relationship and cross multiply to solve there. Khan Academy makes you do that on a couple of the tougher problems, it looked like. Alright, we're going to move to one final problem now. That's problem 5, and this is similar to the last Khan Academy assignment of the week. It's actually pulled directly from the 5th Khan assignment. For our final problem, this time instead of giving you the real world or the word problem linear graph, they describe the situation and ask you to make a graph to match it. So we're going to read that written description, these sentences here. They tell us Siraj took a pizza from the freezer and put it in the oven. The oven heated the pizza at a rate of 7.5 degrees Celsius per minute. So the pizza's getting heated constantly when it's in the oven. And then the pizza reaches the desired temperature of 80 degrees Celsius after 12 minutes. They tell us part 1, graph the relationship between the pizza's temperature and its time in the oven. So first thing, I'm going to dig through here and look for some of the key info that could help me. One thing that I'm going to underline in red at first, they tell me that the oven heats the pizza at a rate of 7.5 degrees Celsius per minute. So we have a heating rate of 7.5 degrees Celsius per minute. I'm circling that in red because anytime I see the rates, they're really describing the slope of the relationship, how much y is growing for every x. In this case, I'm getting 7.5 degrees on the y-axis every 1 growth in minute on the x-axis. I also need to know a little more than the slope. If I'm going to make a graph, I need to know where things start, or at least where they are at one point in time. I'm going to underline this next sentence in purple. It says the pizza reached the desired temperature of 80 degrees Celsius after 12 minutes. And the reason I'm putting it in purple, not green, this isn't our y-intercept. It doesn't start out at 80 degrees, but it is one point in time. So I called it a purple data point because it describes one point on the graph. Specifically, it tells us, hey, at the 12-minute mark, the pizza's at 80 degrees. And you see on the graph, x is measured by time. And this purple sentence is telling us, hey, when the time is at 12 minutes, the temperature better be at 80 degrees. Again, this purple sentence tells us, hey, at the 12-minute mark, we better be at the 80-degree temperature. So for this graph, the first data point is going to end up at the 12-minute mark and the 80-degree mark. So I go to 12 minutes, I go to 80 degrees, and then I'm going to put a nice dot right there. This dot that I just put in red, try again, there we go. This dot that I just put in red here on the graph, where you'll be dragging that first dot, represents, hey, this pizza at the 12-minute mark, it hits the 80-degree temperature. Now I'm going to need to use that rate of change to find more data points. It says the pizza's heated at a rate of 7.5 degrees Celsius per every minute. So I get 7.5 degrees, and I get that 7.5 degrees every 1 minute. Wow, sorry. 7.5 degrees every 1 minute. And now here the challenge is, when I look on this graph, 7.5 degrees every 1 minute, I'd love to go back by 1 minute and go down by 7.5 degrees, but the graph counts by 5-degree things. So I'm going to switch to 7.5 degrees every 1 minute. I'm going to double that to something that makes a little more sense to me. If I double that, that tells me this is the same thing as 15 degrees every 2 minutes. Right? If I multiply this ratio by 2, it shows me, hey, I'm going to be at the 15-degree heating if I do 2-minute gaps. And that works a little better for this number line, which jumps by 5s. 5, 10, 15, 20. You see they mark every other with 10s, which tells me each little line is worth 5. So if I go back by 2 minutes, I'm going to draw a thin line here that goes back by 2 minutes on the x-axis. The pizza would have been 15 degrees colder, or instead of at the 80-degree mark, that pizza only would have been at the 65-degree mark. And right here where I'm putting this next dot, that represents, hey, I just went back by 15 degrees, or lower by 15 degrees, and to do that we had to go back in time by 2 minutes. That would create the rate that we need here, and I'm going to go ahead and draw a line now. It goes through those 2 points to finish this graph. And part of why we create these graphs is these graphs can now tell us data about the pizza at other points in time. For example, part 2 says, what was the temperature of the pizza when Siraj took it out of the freezer? That's at the very beginning before he's cooking. This is really asking us the y-intercept. And now based off this graph, even though at the beginning we didn't know what the y-intercept is, now we can see clearly our y-intercept is right here. That's where the line hits with the y-axis. And this tells us, hey, at the beginning the pizza wasn't even 0 degrees yet. It was negative 10 degrees Celsius. So again, if they're asking you to build your own real-world graphs, I think the big key is to try to find one data point based on the sentences, and then try to use the slope to work out where would that line move from there, where would the other data points have been. Thanks for watching to the end. These were certainly a little more challenging as we got to the end of today's assignment, so if you need any help, please send me an email. I'm happy to jump onto Zoom and work one-on-one with you on some of the later Khan Academy ones. Donald, Michaela, Marco, thank you for your continued awesome work. Alright, I'm signing off now. Definitely feel free to send me emails if you got questions. Have a great day.